Welcome to the next lecture in electrical machines. We were discussing the single phase induction motors, and in this particular lecture we will focus our discussion on equivalent circuit of single phase induction motor. We have seen that the single phase induction motors are conceptualized as single common stator winding but two rotors revolving in opposite direction. So there will be two rotors and there will be only one single stator. These two rotors doesn't mean that it is a physical rotor. It means only that the double revolving field theory that we have discussed, they are basically rotating in the opposite direction. So it may look like the two rotors are there which are revolving in opposite direction, and we have the concept of two double revolving field theory. Then the equivalent circuit is based on double field revolving theory, which is the most fundamental principle of the single phase induction motor that was discussed in the previous lecture. Now let us see how the equivalent circuit can be drawn and what are the special characteristics of these equivalent circuit. First, we will assume that there is no core losses in the network and the stator impedance is given by Z1, which is equal to R1 plus JX1. So here you can see that you have a resistance and a reactance which is in series with the supply voltage. So supply voltage is a single phase denoted by V, and the current I1 is drawn from the source. The resistance on the stator winding is given by R1 and the reactance is given by X1. And you can see that there are two rotor circuit that has been drawn as the equivalent part. Again, I am repeating, this is not the physical rotor. This is based on the double field revolving theory. You will have two rotor concept. Now, if it is observed that the rotor resistance of one part is given by R2 by S and X2, and other part is given by R2 divided by 2 minus S by X2. Whereas Xm represent the flux which is produced in the rotor or the magnetization part. So rotor impedance R2 plus JX2, and this is only the half the actual values. So R2 indicates the rotor resistance and X2 indicates the standstill reactance. So because X2 will change with respect to the slip. So when the rotor gains some speed, then obviously with respect to the speed, the reactance X2 will change and R2 will remain constant. So that is the reason the X2 is defined at the standstill condition, and with respect to the slip, the reactance will change. Xm indicates the magnetizing reactance, which is the flux produced between the stator and the rotor in the air gap. And these values are basically half the actual values which are referred to the stator. Now here we do not have included the iron loss. So without core loss, the circuit is a representation. So you have only the Xm branch where the flux is produced. And we also note that we have used some capital letters and we have also used small letters. So capital letters indicate the full value and the small letters indicate the half values. So this is the equivalent circuit without the incorporation of the core losses. Now, if the impedance we need to determine under the forward running motor condition, and we represent SF equal to S, and this is the actual motor running condition. So in that case, let us see how to obtain the impedance ZF under the forward condition. So this part of the network will give the forward impedance, and this will be giving the backward impedance due to double revolving field theory. So in the forward impedance, we can see that Xm, which is the magnetizing reactance, this is in parallel with the two components, which is one resistance R2 by S and another you have the reactance J times X2. So we can use the parallel concept where the two impedance, when it is in parallel, then we can use Z1, Z2 divided by Z1 plus Z2 concept. So this is the Z equivalent of the forward impedance rotor. So here we are just obtaining the forward impedance. Now, if the rotor backward impedance we need to compute, then in that case, we have to just replace the slip with 2 minus S in the previous equation. So we have 2 minus S representation in the backward impedance, and we have the slip representation in the forward condition. So when the motor is under standstill condition, we know that the forward voltage and the backward voltage will be equal and the motor will be standstill. But during the running condition, the forward voltage always will be 90 to 95% of the supply voltage. So if the supply voltage is V, then under running condition, the majority of the voltage is being taken by the forward running condition of the motor. So the power developed by the motor, if we want to find, then the equation for the power developed is 1 minus slip by slip into the current which is flown in the rotor I2 square into R2. Similarly, if the speed is given in rotor RPS revolution per second, then the torque we obtained is given by 1 by 2 pi n 1 minus slip by slip divided into I2 square R2. These equations are well derived in when we were discussing the three-phase induction motor. Now remember, the induction motor, the actual speed will be ns 1 minus s. So the gross torque that we compute here, if instead of the actual speed, we try to put the synchronous speed, then our equation will be little bit changed. So this is the gross torque as a function of the synchronous speed. This is the gross torque as a function of the actual speed of the rotor. So the equation breaks down as k times I2 square R2 by S, where k is again a constant, and hence the forward and the backward torque from these torque equation can be easily written as defining with respect to the slip. So on the denominator side, we will have the slip for the forward torque and 2 minus slip in the backward condition with a negative sign, because the backward torque is again in the opposite direction to the forward torque. So the total torque will be the summation of Tf plus Tb. Since a negative sign is here, so it will be becoming a negative sign in the backward torque. Now, if we are computing the forward torque in synchronous watt, then in that case, the forward torque, you will be having the current which is flowing in the third branch. So we can write I3 square into R2 by slip. So we have taken by slip because it is the forward torque. If we are computing the backward torque, then the current which is flowing in the fifth branch, and here the slip is 2 minus s. So we have I5 square into R2 divided by 2 minus slip. See, these two equations are one and the same. Only difference is that what is the current flowing in the branches and what is the value of the slip that we are considering. So the total torque again will be Tf minus Tb, because the backward torque is opposite to the forward torque. However, if we include the core loss in the circuit, it is represented by Rc and it is connected in parallel with Xm. So here if you see, Rc is connected in parallel with Xm, and this is the complete circuit of single phase induction motor including the losses. We know that under a running condition, the forward voltage will be very, very greater than the backward voltage, as discussed that it will be 90 to 95% of the supply voltage. So most of the iron loss generally take place in the forward motor. So iron loss will be taken place in the forward motor. It means that when we compute the iron loss, we have to take the voltage of the forward condition. So the current is given by Pi by Pf. Now here, if we see that this part of the network, we can easily obtain the driving point impedance of the ZOF under the forward condition, and this is under the backward condition. So these parts remain the same. So we can still break down the circuit into much better form. Let us see some advantages and limitations of single phase induction motor. So when we talk about the advantages, it is smaller in size and lighter in weight, and it is cheaper in cost. It is highly efficient and it requires less maintenance, have a longer life, and can be designed in a variety of sizes. So since at household and industrial applications, only single phase AC supply is available, so these motors are very much efficient and very much powerful, which are generally available. Now these are available in different shapes and size depending upon the user requirement. So we have seen already in the previous lecture what are the types of single phase induction motors and how they are being constructed. Now when we talk about the limitations for a given frame size and temperature, its output is only 50% of the three-phase induction motor. So three-phase induction motor will be highly efficient when we have the same frame size and temperature. So about 50% more efficiency it has. So we prefer to three-phase induction motor when the supply is three-phase and heavy operation is required. It is not self-started. We have seen this in the previous lecture also, how to make the single-phase induction motor self-starting using the auxiliary winding. So the single-phase induction motors are not self-started. It has a very poor power factor and the efficiency is lower, do not have a starting torque. So we don't have any starting torque. An extra winding is required or extra connection is required to start the motor. For the same power output, these motors are more expensive than the three-phase induction motor. So when we have a choice of selecting the three-phase induction motor or single-phase induction motor, we generally prefer three-phase because they are less expensive and their output will be high as compared to the single-phase induction motor. So single-phase induction motors are generally preferable in household applications where we have a single-phase AC supply and we required motors of different shapes, sizes and dimensions. So this completes the overview lecture series of single-phase induction motor discussed into various parts, and we will see some of the tutorial problems on single-phase induction motor in the coming lecture series. Thank you for now.